Hello everyone. In today's recitation, what we will do is a review of overall topics and things that we covered, an overall review of topics that we covered in Module 3. If you remember, what we started with in Module 3 was the subject or the topic of potential flows. We discussed in that topic that potential flows are mostly known or considered as flows where we call them either inviscid flow, or which means that the kinematics doesn't give rise to any viscous contribution, or inviscid fluids, which means that the fluid or liquid that we are working with has such a low viscosity that we can ignore viscous effects. In principle, the outcome of either of these would be the fact that we ignore the viscous terms in the Navier-Stokes equation. Our governing equation, which is the balance of momentum per unit volume, boils down or gets boiled down to what we called Euler equation. An Euler equation, if you remember from either Module 1 or recent things that you have seen in Module 3, is just the acceleration of fluid elements times density, which is very much inertia per unit volume of fluid elements on the left-hand side, balanced by the sum of the body forces, which is the weight of fluid elements per unit volume, and the gradient of surface forces, which the only surface force we need to worry about in the absence of viscous stresses comes from the pressure field that we have in the flow. We also talked about the fact that we can integrate the Euler equation, and we derived what we called Bernoulli principle from that. This was something that in Module 1 we spoke about, but in Module 3 we expanded that explanation, and we showed that actually in potential flows, the Bernoulli constant, which is the sum of the kinetic energy per unit volume, half of rho v squared, pressure field that we have, which is almost like, if you think about it, pressure times volume is also energy, so this is also some energy per unit volume, plus the gravitational or body force related energy per unit volume, which is rho gz. Some of these three different sources of energy should become constant everywhere in the flow. This is as long as the flow is irrotational in the domain that we are interested in. And speaking about flow being irrotational or being incompressible, we notice something that is interesting. We notice that based on which condition we use for 2D flows, incompressible or irrotational, we can find some interesting mathematical consequences coming out of these assumptions. Let's do one together. We discussed that the flow being incompressible is equivalent to the fact that a stream function, which we denoted by psi, exists. And that means that our velocity field can be written as Vx being partial of c partial of y over partial of y. And the y component of velocity in this 2D flow Vy will be negative partial c over partial x. We also discussed that the moment this definition is there and the stream function exists, we can directly conclude that the velocity field becomes divergence free, or the divergence of velocity is zero, which is what we basically used and defined as condition for incompressible flows. Parallel to that, we also knew that flows can be considered irrotational. And we discussed that being in an irrotational flow is very much equivalent to having another scalar function in our field, which is called potential function and is shown by phi. And we discussed that if phi exists, we can write down velocity components Vx and Vy as the gradient of phi with respect to x and y, respectively. Or in other words, we can easily say that the gradient of this scalar function, phi, will give us the velocity field v. Then we showed that if such an equality exists, automatically we have the curl of the velocity, which is defined as vorticity omega, being equal to 0 everywhere in the flow, which is what, again, is known as what we discussed to be irrotational condition, or what we call these flows is actually the name irrotational flow. Now let's combine them together, and you have seen this already, just as a recap. So let's start from incompressible flows and add to the incompressible flow the condition that flow should be also irrotational. So if it's incompressible and it's also rotational, we show that we actually get an interesting condition for the psi, or the stream function, which will be the Laplacian of psi, or del 2 psi is equal to 0. We also discussed that if you take the other column, which was irrotational flow, and add to the irrotational flow this new condition that the flow should be also incompressible, we reached to the conclusion that the Laplacian of phi, or del 2 phi, should be equal to 0. In other words, we found that the two scalar functions that we defined, c and phi, respectively for stream and potential functions, they both should satisfy Laplace equation if the 2D flow that we are dealing with is both incompressible and irrotational. That was a good motivation for us to use these two functions in a simple mathematical way and combine them with the equations of the flow that we have, so that mathematically it becomes relatively easy to find solutions for potential flows. And the basic underlying idea that we borrowed from some mathematical description was based on the fact that in 2D flows we can deal with the entire plane of the flow, such as x and y, with use of the idea of complex numbers. With the help of complex numbers, we can deal with the entire 2D flow in this manner, that every point has coordinates x and y, and we can define a complex number sitting on that point z being x plus iy. The real part of the position z has the x component, and the imaginary part of it has the y component. At the same time, this also enabled us to find an interesting connection to polar coordinate system, because we know that based on Euler equation in complex numbers, this z can also be written as r times exponential of I theta. So take your favorite description for certain problems that are Cartesian. Of course, you can see x and y coordinate system probably is more convenient. For problems that have some cylindrical symmetry, you can easily use the polar coordinate system description. But the idea was, we had this complex number description for points in a 2D flow, and we wanted to see how we can combine this together with a potential function and a stream function in a way that will give us some meaningful manner or meaningful method or protocol to approach potential flow problems. That will be what we will discuss in the next video.